big idea in nature. It's called the law of conservation of momentum. It's kind of like before how we looked at energy, right? You guys remember the conservation of energy equation? It was really simple, right? In any given system, the energy that you start with is equal to the what? The energy that you end up with. For momentum, it's really simple. The total momentum of an isolated system does not change. What do I mean by isolated system? You're picking a set of objects that are interacting. Because obviously it looks like, for example, with energy, like, oh, we lost energy to friction or whatever. But then if you count for the air, that energy is still conserved. So an isolated system we can define as not having an external force. So it doesn't mean that there's no forces. There's just no external force. So the initial momentum before a collision is equal to the final momentum after the collision for all the objects involved. And there's a whole bunch of famous examples. So the first one is this little toy called a Newton's cradle, which you've all seen before on different toys and things. We've looked at that for Newton's third law. And actually, it is a consequence of Newton's third law. For every action on an object, there's an equal and opposite what? Reaction force on the acting object. So notice, if we treat this whole thing as a system, if I send in 1 unit of momentum, how many units of momentum do I get out afterwards? 1. That's awesome. What if I send in 2? Wow, I get 2 out. That thing is totally cool, other than if I shake my hand. I'll try not to shake. If I send in 3, how many do I get out? 3. Wow, what if I send in 4? I get what? 4. What if I send in 5? Well, just get 5 there, right? So the coolest way to see this, though, is if I send in, let's say, 3 on one side, 2 on the other. So what if I send in 3 and then 2? And this takes coordination. There we go. That's okay. Let's say I do a 3-2 split, right? So there's 2 things that can happen. The Newton's cradles, the balls can either just bounce off each other, or they can exchange momenta, is a way to think of it there, right? So what do you think? What would be the most logical thing to happen? If I send in 3, I'm going to get out 3, exactly. I'm not going to have 3 bounce back. So it's going to look like just the middle one is swapping, but really what's going on is it's an exchange of momentum. The impulse is the same on the collisions of the balls. The forces must be equal and opposite in magnitude and direction there, and the time of impact is also the same there. So the way we can break this down in terms of mathematics to explain it, to make it a little bit easier, using Newton's third law, as we just said, because you can't have a force by itself. For an acting force on a body, there's an equal reaction force on the accompanying body. The momentum lost by one object is simply the momentum gained by the other. You don't have to write down this big statement. This was just breaking it down for you. So how do we apply this here? It's real simple here.